to trying to figure out what's going on in here. On this edition of Scientific American Frontiers, we're exploring the brain. We'll start with a man with two brains. It's really like two different people. Then we'll peek inside a brain while it's storing a memory.
Oh, it's cold.
We'll discover how easily memory can be fooled.
This is horrible.
And we'll eavesdrop on my brain when I'm dreaming.
I am not checking into this hotel again.
I'm Alda. Join me now for Pieces of Mind. We've gone to extraordinary places and done extraordinary things in making Scientific American Frontiers. But there's nowhere we visited that's more extraordinary than our destination now. Inside the human brain. This brain is now no more than 3 pounds of preserved tissue. But once it held a mind. A mind that was filled with 1,000,000 memories of a first ice cream cone, a vivid sunset, a bicycle, a kiss. It learned a language. Maybe 2 or 3. It felt rage, pain, joy, fear, love. It dreamed of flying, of falling, of forbidden things. For the briefest moment, it experienced death. We still know almost nothing of how the brain works. But in the next hour, we'll visit with researchers who are finally beginning to see inside the brain while it's dreaming and thinking, learning and remembering. You're in for an experience which could change your brain forever. We began our journey into the human brain here on the campus of Dartmouth College in New Hampshire. I'd come to meet one of the world's leading brain scientists, Mike Gazzaniga, and a man he's worked with for over a decade. A man with 2 brains. You've been working a long time with Dr. Gazzaniga?
14 or 15 years.
It doesn't seem like that long, does it?
Well,
the collaboration began when Joe had surgery. And you had this procedure to correct an epileptic problem,
yes.
Is that right?
Trying to stop the seizures. I was having seizures like every day or so, or sometimes 2 or 3 a day.
To control Joe's epileptic seizures, a surgeon severed the connection between the 2 halves of his brain. Cutting the corpus callosum like this prevented the spread of the electric storms that caused his seizures. But it also prevented the left and right halves of his brain from communicating with each other. In the years since the operation, Joe's epilepsy has been under control. He now earns a living at an egg farm, and in his everyday life, he's largely unaffected by the fact that his left and his right brains work independently. Do you feel any different when you think about something than you did, any differently from the way you felt before the procedure?
It's just got a backup brain, that's all.
That's something everybody could use, right? I found out how true that was right away when I was asked to draw a different shape with each hand. In a brain like mine, roughly speaking normal, at least all in one piece, the left half of my brain controls the right side of my body, while the right brain controls the left side.
Oh, no.
But because the 2 halves are connected... Nothing wrong with that. Getting each hand to work independently isn't easy.
Well, we're seeing the fact that Alan's hemispheres are connected, and that the motor messages from one are confusing the motor messages in the other.
I was just drawing an upside-down duck.
Okay.
But when Joe is given the same task, his 2 hands operate as if controlled by 2 separate brains. What's happening is that each half of Joe's brain is given a separate instruction. He's asked to fix his eyes on the cross in the center of the screen. Anything flashed to the right of the cross goes only to his left hemisphere. Things to the left go to his right hemisphere. Because the 2 don't communicate, each hand does only what its half of the brain sees.
Wow, look at that. It's really like 2 different people doing the same.
That's right.
Same task.
That's the idea.
Okay, Joe, I want you to keep your hands out in front
In
of
an
you.
experiment that's now a classic in brain research,
Mike Gazzaniga, over 30 years ago, used a similar setup to find out if the two halves of the brain are specialized to do different things.
Ship.
Joe is being flashed a word only to one half of his brain. Words flashed to the right
Storm.
are seen only by his left brain, and Joe can report seeing those words just fine.
Piano.
Good.
But when a word is flashed to his right brain,
Didn't see that.
Okay. So I'm going to ask you
but now watch what happens.
to draw that with your left hand.
They got me lost.
Why don't you try drawing another picture of it over here, if that will help you.
Oh, phone.
Oh, okay.
Durr.
It's almost as though somebody has given him a secret communication.
That's
and
right.
now he knows that it's a telephone. But up until then, he was blind to it.
Exactly.
When Gazzaniga first did this experiment, it instantly proved that the ability to speak resides almost exclusively in the left hemisphere. Not until he sees what his right brain is drawing is Joe able to name it.
He said church, didn't he?
After looking at the picture.
But he had to figure it out about as long as we did. That's really interesting. It's a picture here of somebody communicating almost with another person.
The communication is not occurring inside the head, it's occurring out on the piece of paper.
Yeah.
Blob. I really don't know.
You want to draw a little bit more?
So far, Joe has been seeing only one word.
Cat. That's a cat
Things get
sound.
even stranger when he's flashed two words, each to only one half of his brain.
The right hemisphere saw toad.
Yeah.
And so his left hand draws a toad.
So there's the toad.
Oh, it's a toad.
And this time, I was able to guess what was coming.
Will
Now-
we put a little three-legged stool in there later, or what?
Joe's speaking left brain saw a stool. Saying the word lets the hand that's controlled by his right brain in on the secret.
That's great. That's really interesting. And if he had seen that with the corpus callosum intact, he would have drawn a toadstool.
Right.
Not a toad and a stool.
Right, exactly the point. I've been doing this for 35 years. Yeah.
And
It gets me every time.
Yeah, it must. It must.
This time, instead of naming the word, I want you to point to the word.
Again, Joe sees two words simultaneously. Bell goes to his non-speaking right brain. Music to his speaking left brain. When asked to point to a picture of what he saw, he chooses Bell. But when asked why,
Yeah, why'd you pick that one?
Music.
Music?
and when asked to explain,
It was music and bell, and it was a few minutes ago, last time I heard any music was coming from the bells out here,
Uh-huh.
banging away.
So the bell's
Yeah.
outside here.
So, but good enough answer to me.
what's extraordinary is that Joe's speaking left brain concocts a plausible story of why he pointed to Bell, even when some of the other pictures more obviously represent music. Gazzaniga believes this determination to find cause and effect, this desire to explain, is the left hemisphere's most marvelous property.
One of the unique things of the human brain is this need to interpret why two events occurred. What was the antecedent of this? What caused this? And if you can imagine that a species like us that has that little chip in its brain that asks those questions is going to survive rather well, because it's going to figure out more about the nature of the world than a species that doesn't have that.
Okay, Joe, I want you to keep your hand...
But as I was about to discover, the right brain has a very useful survival skill all its own.
Figure.
What do you think will happen here?
So for you, we're doing a live experiment. Never done it before.
The experiment involves the 16th century Italian painter Arcimboldo, who made faces out of fruit, flowers, meat, even books. From other research, there's reason to believe that the ability to recognize faces is located exclusively in the right hemisphere. So Mike wondered if Arcimboldo's paintings would look different to each of Joe's two brains.
So will his left hemisphere say, I saw a potato, I didn't see a face? And will his right hemisphere say, I saw the face, and not comment on the fact it was made out of a potato?
You're going to see a figure followed by a choice of two words.
If this works, it'll be terrific, but we'll see. So here it is live.
Okay?
The first painting goes to the right hemisphere. And Joe points to face.
Down.
The next painting goes to his left brain. And this time he points to fruits. Mike seemed pleased.
Are you having a moment?
This is too good.
Again to the right brain, and Joe sees it as a face.
Point it down.
But to the left brain,
Face made out of books.
Point it up.
Pointed at books.
Are you happy with what you're seeing?
It's unbelievable. He's doing it. You see that?
It's good. It's going so fast. It's shifting from left to right so fast. I can't keep up with you. You're used to looking at this.
When you show him a face in the right side, the left hemisphere,
Yeah.
he's focusing in on the elements that made up the face.
Yeah.
When you show him the exact same picture in the left field, going to the right hemisphere, he's focusing on the face and not the elements.
And not the elements. If you came down from another planet and you saw faces and vegetables, you might not think there was much of a difference among them. But the brain seems to be made up in a certain way to say faces are very different from other objects.
That's right.
And one side of the brain specializes in faces. huh?
Exactly right. Exactly right. It is an adaptation that we have to detect upright faces. It's a very important. You can imagine in an evolutionary time that all of a sudden you have the ability to detect quickly an upright face. You want to read the expression on that face. You want to know if it's friend or foe. You want to have a set of questions about that face.
the right brain might be skilled at recognizing faces. But when it comes to what gives the human mind its power, the ability to reason, to invent, to interpret the world around it, Mike Gazaniga's 30 years of research has taught him which hemisphere he wouldn't want to be without.
The old phrase around our lab is, don't leave home without your left hemisphere. That's where the action is.
The clarinet player is Jim McGaw. The tune, As Time Goes By. His passion, the mind, and how it's shaped by memory.
Everything that we do as humans depends upon our memory. Your notion of your own past is nothing but a memory in your brain. Something changed in your brain. You and I live in a world which is about a half a second long. That's the immediate experience. And what happened 2 minutes ago that you think is still here is gone except in your brain.
This rat at the University of California, Irvine, is about to get a better memory thanks to Jim McGaw. There's food at the end of 4 of these arms. Entrances to each of the other 4 are blocked by a plastic window. Once the rat has eaten the available food, the windows are removed and food is placed in the previously blocked channels. After several trials, the rat learns to enter only the newly opened arms, ignoring the old ones it had already cleaned out. "18 hours later, however, the rat has forgotten the secret and checks out the old arms as well as the new. But this rat is getting some help. A shot of adrenaline immediately after learning the task. This time, after an 18-hour absence, his memory of the maze was as good as new.
He remembered where he had been before and only went to the arms that he hadn't been to. So he performed the task very well, perfectly, 100% performance.
Adrenaline is the hormone responsible for the fight or flight response, the surge of energy we and other animals get when we're threatened. Jim McGaw's experience with rats suggests the adrenaline rush is doing more than allowing us to run fast.
It also would be a very good idea to be able to remember where the predator was and what happened so that the next time that animal can avoid that situation. or to minimize the probability of being eaten the next time. So the same hormones which were involved in generating the fight or flight response, we now have discovered work on the brain so as to make stronger memories.
So what would happen in a stressful situation, which for rats means having to swim, if somehow adrenaline is removed from the picture? This rat is trying to find a transparent underwater platform. Eventually, he has to be shown where it is. Three days later, and he finds the platform quickly. Like his colleague, this rat has also been shown the platform. But moments later, he gets an injection of a drug, a beta blocker that blocks the effects of adrenaline. When this rat's tested 3 days later, it's as if he's never been here before. So for rats, adrenaline seems central to making stronger memories. But what about the rest of us?
What we need to do is to have two different stories.
Jim McGaw is collaborating with Larry Cahill on an experiment that involves a single set of slides telling two very different stories.
A boy and a mother leaving home. They're going to visit father who works in the hospital.
If I could have your left hand
The
out,
subject
like
is told his emotional reactions to a story are to be measured. In fact, this device isn't hooked up to anything.
Okay. A mother and her son are leaving home in the morning.
The story he hears is bland.
She is taking him to visit his father's workplace. The father is the chief laboratory technician at a nearby hospital.
It concludes with mother and son coming across a fake car accident being used in a training drill.
Special makeup artists were able to create realistic-looking injuries on actors for the drill. Okay, that was very good. Now, the last thing I would like you to do today is to rate your emotional reaction to the story you just saw on a scale of 0 to 10.
Probably about a 2.
Okay. She's taking him to visit his father.
This subject is hearing a very different story.
While crossing the road, the boy is struck by a runaway car, which critically injures him. Specialized surgeons were able to successfully reattach the boy's severed feet. I'd like you to rate your emotional reaction, your personal emotional reaction to the story you just saw.
A 7.
A 7, okay.
2 weeks later, the subjects are given a surprise memory test.
You were told that the father's occupation is a school teacher, a surgeon, a laboratory technician, a hospital custodian.
A laboratory technician.
Memories of the emotional story are good.
Next question. You were told that the father's occupation is a school teacher, a surgeon.
Memories of the boring story are poor.
I think it was the hospital custodian.
Hospital custodian.
So far, so good. But is it adrenaline that's making the difference?
There's the pill, and there's some water right
This
there.
subject is taking a beta blocker to block adrenaline right before getting the emotional version of the slideshow.
While crossing the road, the boy is struck by a runaway car, which critically injures him. At the hospital, the staff prepare the emergency room.
He still rates the story as highly emotional.
I'd say about a 7.
7? Okay, very good.
But when he's tested 2 weeks later, his memory is as poor as those who heard the bland story.
Surgeon, a laboratory technician, or a hospital custodian?
Surgeon.
Surgeon? Okay. Despite the fact that their emotional reaction to the story a week earlier had been normal, they didn't experience the enhanced memory associated with the emotional reaction that the placebo controls did. So what we seem to have done, what we think we have done, is we snapped the relationship between an emotional reaction and enhanced long-term memory.
Okay, and let's go.
The Irvine team is now trying to pin down the relationship between emotion and memory by looking inside the brain as a memory is formed. Shannon is left alone to watch 30 minutes of unpleasant images while glucose is injected into her bloodstream.
What I'd like to do now is to lay you down.
This machine, called a PET scanner, produces an image of Shannon's brain, revealing where most of the glucose was being used, and so which part of her brain was working hardest. And the region that was most active is an almond-sized structure called the amygdala. What's more, in tests like this with several subjects, the brighter the amygdala, the better their memory of the film 3 weeks later. It's the beginning of an explanation, Jim McGaw believes, of why we remember emotional events. Activated by the hormones the emotions produce, the amygdala sends a message to the rest of the brain, as if to say, this information is important. Don't forget it.
Life goes by, trivial things happen to us. Important things happen to us. Now, it would make a lot of sense, wouldn't it, because we have a brain that probably has some limited capacity of some kind. Wouldn't it be nice to have a brain which stored to a more intense extent those things that are important, and to a lesser extent those things that are trivial? We have a brain that does that. And it's emotions that create the relationship between the importance of an event and how well we remember that event.
Start seeing bits and pieces of their life.
What I didn't know one pleasant morning while strolling with Dan Schachter was that in collaboration with my scheming producers, he was setting me up for a test of my memory.
Now we're just going to witness a simple picnic scene, and we want you to pay attention to how often either of the folks gets up and down. So whenever someone gets up and down, you just make a mental note of it.
Okay. I knew Dan Schachter to be a noted memory researcher, but this picnic was a surprise.
Would you like some pasta?
Yeah.
Oh, good. I love to watch people eat. Although Dan had told me to keep track of how many times the picnickers stood up, I suspected there was more to this little scene than that. But what? I wasn't to find out for another 2 days that the picnic was part of a carefully choreographed attempt to implant false memories into my brain, to make me remember as real things I'd never seen. At the time, it was like trying to keep track of a very bad play while sitting uncomfortably close to the author.
Ooh, it's cold.
After 10 bewildering minutes, the picnic mercifully came to an end.
Very nice. Well done.
Very nice.
Well, it could use a little more high drama here and there.
Yeah, no, but it doesn't lack for slowness. It's good.
At this point, I was politely asked to leave. The scene was played over for a stills photographer, but this time it included things that had never happened while I was there.
Ignore the sun.
Which means I also missed Dan Schachter's basic premise, that memories are malleable.
One of the things that we know about memory is that it's not fixed at the original experience we have. The way we talk about the event later, the way we think about it, can affect, improve, or sometimes change our memories, and photographs are one everyday source of reviewing past experiences that may have a potent effect on memory, and we're interested in exactly what that effect is.
Great, thanks.
I want you to look at each of these for about 10, 20
2 days later, I was in Dan Schachter's office at Harvard University, looking at photographs.
Get cut out, is it well-centered? For each photo, I'm going to ask you for a 1 to 5 rating.
Oh, see, part of me is trying to figure out what this is really a test of. I'd have to say, 4 to 4.5.
Okay,
It's a nicely composed picture.
I didn't believe this rating ploy for a minute, but I graciously played along, even when I knew the photos were of things I hadn't
I
seen.
take it you don't want me to mention whether or not this was a picture of something that happened or not, because this never happened.
Right, we're not concerned with that right now. We're just concerned with your...
Showing how smart I am.
Right.
In all, I looked at about 20 photographs. Finally, the moment I'd been anticipating,
Fishing pole.
the test. No. The question is, did I see these things at the picnic or not?
Umbrella.
No umbrella, no.
Potato chips.
No, the potato chips were in the picture. Well, I remember them in the picture, but I don't remember them on the site.
Okay, so you're going to call...
I was doing fine until...
nail file.
Yes, I think I remember her filing her nails, although the picture is also vivid in my mind. But I think I remember her filing her nails, too.
Kite.
No kite. No, there was no kite. There was a kite in the picture, but that's it.
A man's cap.
Dan was obviously trying to confuse my memory of things I'd seen for real
I think he wore a cap.
with things I'd only seen in the photographs.
Well, see, I think he was wearing a cap in the photographs, and I remember when I looked at the photograph, there's something wrong with this picture. I don't think he wore a cap, no.
A bottle of water?
Yes, there was a bottle of water.
Uh-oh, this would come back to haunt me.
Folding chairs?
No.
No, no way. Pasta?
Yes. You think I could forget pasta? Come on.
It's over.
That's it?
That's it. It's out of
So
your
it had
system.
nothing to do
No
with how
more.
many times they stood up.
Well, that was just to get you to pay attention to what was going on in front
That's
of you.
why I paid attention to everything else. Now, what I'm really interested to know is, were you able to place in my memory things that never occurred in real life
Yes.
by using the photographs? You did?
We
You
did. Even though we told you, you knew what the game was.
Yeah.
You knew that some of the things that we were showing you in the photographs had never happened. Despite that,
This is horrible.
one was the nail file.
Yeah.
That was only in the photo.
You know, when I first saw the nail file, there was this little uncertainty. Is that real or isn't it? And then, a second later, I was sure I had seen it.
In the final tally of 8 things that appeared in the pictures only, I wrongly remembered 2 as having been at the picnic, the nail file and the bottle of water. The photographs had somehow lodged in my brain right along with my memory of the picnic itself, and I couldn't tell which was which. To understand how this can happen, we have to first understand where in the brain memory is located.
Is it possible to point to some place on the brain and say that's where memory is?
Well, there's no one place. There's no one place I can point and say, there's your memory for high school graduation, and there's your memory for having eaten breakfast yesterday. Instead of being in one place, many of us believe that the memory is kind of scattered in different parts of the brain.
The idea is that memory consists of all the bits and pieces of an experience, the sights, the sounds, the emotions, with each fragment stored in areas of the brain responsible for handling that particular sensation. So sounds are stored in the auditory cortex, sights in the visual cortex, and so on. Keeping track of what's where is a region of the brain called the hippocampus, which functions as a sort of index for our memories. Recalling an event means reassembling all those bits and pieces. It's not like replaying a videotape. It's more like shaking a kaleidoscope. With every shake, every recall, the pieces fall together anew, sometimes, as in my memory of the picnic, including bits that don't quite belong.
Okay, so here's the first list.
Dan Schachter recently wondered if he could tell the difference between real and false memories by peering into the brain while it was remembering.
Coarse, uneven.
12 people heard word lists like these, and they had to remember as many of the words as they could.
Rider, gravel.
What's sneaky about the lists is that while they're each united by a theme, they don't contain the most obvious word.
Bed, rest, awake, tired, dream, wake, snooze, blanket, doze, slumber, snore, nap, peace, yawn, drowsy.
Sleep, doze, bed.
There, right off the bat, I said sleep, but sleep wasn't on the list. Again, I'd been given a false memory.
Bed.
The 12 experimental subjects all got PET scans while doing this test. Recalling both true and false memories mostly involved the same bits of brain, especially the hippocampus, the index region. But while the true memory lit up the auditory cortex, the false memory didn't. So even though the subjects reported hearing the words that weren't there, their brains appear to contain no trace of the sounds of the words.
So in a way, you really can look inside somebody's brain and tell whether they're having a true memory or a false memory under certain conditions.
Under certain conditions, within this one experimental paradigm in a group of 12 people, we were able to see some differences between true and false recognition.
Dan Schachter emphasizes there's a long way to go before this first faint trace of a false memory can be turned into a practical test that could be used, for instance, in a courtroom. Meanwhile, discovering how easily my memory can be tricked was less than enough for me.
what I think that this really brings home to me is it's very important to say not, this is what happened, but it seems to me that I remember this is what happened.
I think that's a very important lesson.
My brain is about to enter an altered state of consciousness. At least, that's the plan.
Uh-huh. Hello.
How are you?
Now what, I sit here?
Yes, please.
All I have to do is go to sleep.
Okay. The first thing that we're going to be doing tonight is putting electrodes on so we can measure your electrical activity and know your stages of sleep.
What's that?
It's called collodion. It's very similar to airplane glue. And what this
Airplane glue in my hair. As it turned out, only the first of several indignities that lay ahead during my night as a research subject at Harvard University's sleep laboratory.
I don't want to rush you, but I'm falling asleep.
Are you really? Good.
The study I'm joining is to find out what happens to our minds while we're dreaming.
Okay, and that's the last electrode.
Like most people, I've always been fascinated by dreams, my own especially. How do our brains come up with that stuff? Even more interesting, why? My night began with a test of the state of my brain.
You ready? Can you see it?
The task is to spot if the second of two words flashed on the screen is a real word. Sometimes the second word seems to be related to the first. When it is, and if my brain makes the association, then I'm usually able to decide if the second word is real or fake more quickly. So by measuring my reaction time, the test can tell how good my brain is at making associations.
Bed. Bed. Ah, good.
And just climb right in.
The only association I was interested in right then was between bed and sleep. Not so easy when you know a stranger is eavesdropping on your brain.
Alan, I need you to lie quietly with your eyes closed. Okay, if you could blink 5 times, slowly.
This is to
and
check the
really
electrodes near my eye. They'll be looking out for REM, R-E-M, the rapid eye movements we all make when we dream.
Great. Okay, you're all set. You can go ahead and get comfortable and have a good night's sleep.
So if you'll excuse me, I'll leave you in the care of Jen Holmes, while I try to sleep with wires pasted on my face and glued to my scalp.
Well, now he's moving, getting comfortable. And you'll typically see some kind of movement when people first start to fall asleep. The top 2 lines represent his eye movements, and we see that they start a gentle rolling pattern as he falls asleep. The next 2 lines down are his brain waves, and we see that as he falls into real sleep, they start to get spikier. He's now officially asleep. Our experiment calls for him to do the word association test several times during the night. One of them when he's asleep, but not dreaming. That's what's happening now, so I'll go wake him up. Rolling over.
No, falling asleep here. I am not checking into this hotel again.
Well, after that, my night went to pieces. Every time I drifted off and started to dream, I'd think, oh, good, I have to remember this, and I'd promptly wake myself up. By 6 in the morning, Jen had been joined by her boss, Bob Stickgold, and it began to look like we weren't going to find out what my brain does when it's dreaming.
Since about 2:30 this morning, he's been having a hard time sleeping. He'll go to sleep. He'll sleep for 10 or 15 minutes here. You can hear the pens slapping around. He's rolling around in bed now. And he's been doing that for hours now.
But then, when it was almost too late, I began drifting into a dream.
If we wake him up right now, we got about an 85% chance, 90% chance of getting good REM reports. So what we want to do is wait until he gets another burst. There's some more right there. Look at these. These are really good eye movements. These are fast and they're big. So I think we should go in there now and see what we can get.
I was being propelled by the solar wind, but the wind wasn't behind me. I was going toward the sun. And then I was flying over Berlin, and I remember thinking that this was called Nightgown over Germany.
It's only about 6:30. It's still early.
Oh, it's still early. Oh.
Yeah.
Well, let's try.
Let's try. Okay. Pleasant
Well,
dreams.
With one dream in the bag, I felt better about trying for another, so that once again I could be awakened for that exciting word association test.
So how did it feel to you that you slept?
How did it feel that I slept?
Yeah.
I had a worse night of sleep at a truck route in New Zealand.
Really?
Yeah, it was an interesting...
By now, all I wanted was a little breakfast and the airplane glue out of my hair. But I was also curious, of course, about the tests I'd been taking. What did they have to do with dreaming?
That's not good.
Most dream researchers believe that during REM sleep, the normal signals to the brain from our bodies are cut off. Instead of receiving inputs from our eyes and ears, the visual and auditory centers are flooded with signals surging up from the more primitive regions of the brain. These signals, the theory goes, are completely random and meaningless.
I said to myself, because first I went
But dreams, of
out
course, seem to make
blind,
sense,
but have an
at least at the
out-of-body
time.
experience. The wonderful part about it was I went out through my nose. See? So then I had all these words I was hearing.
So the key question is, where do the stories of our dreams come from? According to Bob Stickgold, we simply make them up as we go along.
I'm a little thick this morning because I had this funny night's sleep. I still don't quite get how you arrive at the conclusion that something in the brain is supplying story and meaning and coherence to these random images, and not that they're coming up in a more coherent way already.
If you look at your dream, I mean, there you have this thought of, gee, it's going to be an out-of-body experience. And first of all, it goes out through your nose. I'm sorry. It's just hard for me to believe that someone scripted that for you to do. You were just thinking, out of body. How am I going to get out of body? Help me, somebody. How can I get out of body? And something in your brain says, now your nose.
So during dreaming, our brains are scrambling to make sense of nonsense. Here's where the word tests are revealing. Because subjects awakened from REM sleep are quicker at making associations between the words than when awakened from non-REM sleep, or even when they're wide awake during the day. It's as if during REM sleep, our brains are primed to put together stories from random images and feelings.
Our guesses, and it's truly just a guess at this point, is that the brain is just trying to keep up with these random inputs and trying to use everything it knows to make some kind of sense out of it.
Well, welcome to your home for the week.
That might be how we dream, but it still leaves the question of why. This experiment, being conducted in the sleep lab at Trent University near Toronto in Canada, is suggesting dreaming helps us learn.
Okay. All set. Okay. I'll see you in the morning. All right.
Lara Sylvester is spending 4 nights of her summer vacation here. At least she gets to sleep in peace. The aim of the study is to see how active her eye movements are during dreaming while she's in a relaxed, summery frame of mind. Recording and counting her eye movements is researcher Carlisle Smith. Summer's over, and Lara is studying hard for her final exams. Now her brain is in high gear, right up through the finals themselves. Her mind still buzzing from all that learning. Lara again gets to sleep in the lab. And now the number of rapid eye movements during her dreams is strikingly different.
For some people, there's almost a doubling of the number of eye movements after they've had intense learning activity than when they've been just in a summer mode, for example.
This discovery led Smith to wonder if the extra eye movements during learning are useful. Do these apparently more intense dreams actually help us learn?
1 unit woof.
So he set up an experiment to see if learning a complicated logic game was affected by how much dreaming a person does. The game is baffling enough to explain, let alone play, but it involves making letter combinations according to complex rules.
A or E to start off with. You can then make one final gigantic messy woof.
The game is a tough test of logical thinking. The students' skills at the logic game were tested, and then they were given a much simpler memory test. After seeing pairs of words, they were shown one of them and had to remember its partner. Then some of the subjects, this is Catherine, got to have a night's sleep almost as bad as mine.
What we're trying to do is deprive them of 2 REM periods. So once she goes from stage 2 to REM sleep, I will go in and wake her up. Catherine, good morning. What?
Once awakened, Catherine is kept awake for 5 minutes by a math task to make sure she doesn't slip back into her dream. Other students were the experiment's controls, either being awakened when they weren't
I
dreaming
need to get up for a few minutes.
or getting to sleep through the night in peace. A week has passed, and it's time for the memory test again. Catherine, deprived of dreams, doesn't do as well as she did before, but then neither do any of the subjects, even those whose night was undisturbed. But then came the logic task, and this time there was a significant difference between the dream-deprived and the dream-indulged.
Any tasks where it just seems to be straight memorization that's involved don't appear to be vulnerable to sleep loss, REM sleep loss. But tasks where some kind of more understanding is involved. You not only have to memorize some rules, but you have to be able to apply the rules. That kind of material is vulnerable to REM sleep loss.
Carlisle Smith now took a daring leap. What if people could somehow be prompted to learn during dreaming? A new batch of student volunteers hear a loud clock while learning the logic game. When they're tucked in for the night, some of the subjects now wear earphones, and whenever their eyes are darting most rapidly, they get to hear ticks reminiscent of the clock. The idea is to see if the ticks remind the dreamer of the learning task right in the middle of her dream. The results were startling. Students who heard ticks during active eye movements proved far better than controls in learning the logic task, suggesting that being reminded of a problem during dreaming helps us tackle it. All in all, finding out that not only is my mind more capable of mental leaps when I'm dreaming, but that I might actually be doing something useful with that ability, made my night at the sleep lab seem worthwhile, at least in retrospect. It's nice to know that something we spend perhaps 1/10 of our lives doing is more than simply nightly entertainment. For our final story, I'm once again having my head examined, this time in the lab of Helen Neville at the University of Oregon, Eugene. You know, I think after this show, a lot of people will be wearing these.
We've had many requests for extra hats after our subjects see how fetching they are.
Yes, a lot of people want to wear them out in the street.
Oh, absolutely.
like cute little suspenders.
We don't want it to slip now.
Are we afraid my helmet will, like, whip off if I turn my head too fast?
When we turn the propeller on,
yeah.
We want to make sure you don't go anywhere.
I'm going to ask you some dignified questions while I'm wearing
That button.
Now a special gel is added to each of the 32 electrodes in the hat.
F7, okay. Yep.
The gel helps make electrical contact between the electrodes in my head.
Too high.
That's great.
It has to be firmly worked into place to be effective.
Yes, well, I think you drove the gel right into my scalp.
Well,
So you're making
got a
direct
good
contact
reading
with the
there.
neurons there. I think you'll get a very good reading.
Now let's go to the right hemisphere, T6.
62.9. I guess it's time to jam another Q-tip in my brain.
That was the warm-up.
Go in, slowly.
But for the actual experiment, I'm going to have to plug in, get comfortable, and relax. You want to hold this?
No, this one.
We're going to check first that we have good contact from all the electrodes and that we can see good, clean signal out of your head. And then we'll begin with the experiment.
Okay.
Okay.
I'll just relax.
When they're listening in on brain waves, neuroscientists like Helen have to get their subjects to reduce their muscle activity to a minimum so the faint signals from the brain can come through.
Okay, Alan, this looks really good. Keeping your eyes nice and still, your muscles are really relaxed. Keep that up.
Helen studies where in the brain we process language. My task is simply to follow each sentence and register whether or not it makes sense. That one seems okay. Here's the next. Sue shared her candy with her best boat. Well, that's nonsense. But actually, the task itself isn't important. That's just to hold my attention. In fact, the system is continuously checking every electrode to look for tiny changes that might coincide with each new word flashing up. Averaged over hundreds of subjects, these signals show where in the brain different words are processed. The result is fascinating. Vocabulary words like light, daytime, candy, boat are processed in different places in both left and right hemispheres. But grammar words, her, with, the, in, are concentrated in parts of the left hemisphere. So for language, different parts of the brain have different jobs. That's true at least for adults. The question Helen Neville asked was, is the same true for children?
Hi, Daddy.
14-month-old Dossie is at the stage of life when we rapidly acquire language. To find out what's going on in her brain, she needs to put on that charming hat with the electrodes. This time in a fetching shade of green.
Oh,
Dossie, however, has other ideas. I can't say I blame her.
oh.
Well, how about the blue one?
See? It's pretty.
Or maybe the yellow will do the trick.
Okay. Oh, she's taking it off Ernie. Liberate Ernie.
Fortunately, Davy, her brother, couldn't see what all the fuss was about. With stuffed animals to hold his attention, he settled down to listen to a series of words while the system measured his brain's response.
Bottle. Carbon. Cat. Diaper.
The result, once again averaged over many subjects, looks completely different from the adult pattern. Very young children process language all over the brain. But then pretty soon, by about age 4 or 5, the typical adult specialized areas are emerging.
Mechanical thing of the number of...
This kind of result has important implications for education in general.
Are there things we should be doing sooner when we educate children?
We don't know when the critical time windows are. When learning math, learning music, learning science, different kinds of learning would be optimized. But I don't have any doubt that there are such critical windows of opportunity. We just need to do the research to determine when they are. What we do know is that from the point of view of language learning, early is better.
For people who learn more than one language, the early locking in of the brain's language areas makes a big difference.
Let me see, got 5 minutes.
Arthur Goh, for example, speaks fluent Chinese and English.
Where were you born?
Singapore?
How old were you when you started learning English?
About 3 or 4.
So in school?
In school.
So while English is Arthur's second language, he learned it when he was still young. When he's tested, his brain's response to English is indistinguishable from that of a native English speaker, with the same specialized areas for grammar and vocabulary.
Where were you born?
I was born in Yat Yat, Vietnam.
Yet, yeah?
English is also Nick Hong's second language, but he didn't start learning it until age 10. And when responding to English, his brain looks different. There's no single grammar area. Nick ran up against a limit that confronts all late learners of languages. In my case, I started studying French in my teens. I got really serious about it in my late teens, and I thought I could speak pretty well. What were the things limiting me?
The sound of the language and the grammar of the language are the parts of the language that suffer most from delayed learning of a language. So you probably speak with an accent in French. People will probably tell you that. And your grammar probably isn't perfect. On the other hand, you probably have a huge vocabulary.
Nobody who learns a language after childhood can expect to speak it perfectly.
Old King Cole was a merry old soul.
And a merry old soul was he.
So don't blame the speakers. For grammar and pronunciation, at least, you can't teach an old brain new tricks.
He called for his pipe, and he called for his pole.
And he called for his fiddlers 3.
Every fiddler, he had a fine fiddle.
And a very fine fiddle had he. Tweet, tweedly-dee, went the fiddlers.
But there's none so rare as can compare
with King Cole and his fiddlers 3.
If I didn't have words, I probably...
Back in the lab, I met another of Helen Neville's test subjects, Dean Gable.
When did you learn to sign?
I learned when I was 4 years old.
What brought that about? How did you learn to sign?
When my parents found out that I was deaf. They found out that when I was 2, and they decided to send me to the deaf school when I was 4 years old. And there is where I learned to sign.
When Dean's response is tested in the same way as for a spoken language, the result looks like that of any other first language, with typical grammar and vocabulary areas. That makes sense because he learned sign language while still young. But take a look at this. It's a peripheral vision test in which Dean has to detect the flashing squares on the edges of the screen while concentrating on the one in the center. When his brain response is mapped, it shows he's using both the normal vision processing area and large sections usually devoted to sound. Of course, vision takes on critical importance when you're deaf. When I took the same test, my peripheral vision wasn't as good as Dean's, and I didn't use that extra processing area in the brain. This is the flip side of development in the young brain. Not only is it locking in particular parts for specific functions, but it can also invent new uses for sections if necessary.
That's just amazing that you've got this kind of, the brain is kind of malleable like a piece of clay in a way. It's not so hard and fast as at least I thought it was.
That's right. There's no doubt about the fact that there are very strong biases or likelihoods according to which the brain will develop. That's why in 99.9% of all the people, this is visual brain, this is auditory brain, this is the part that's important for touch, this is the part that's important for language. But these strong genetic biases can be changed, they can be modified within limits, within time limits. This is a sheep's brain.
Our knowledge of what's going on inside all brains,
Of a cat.
cats, sheep's, or people's, is still limited.
It's a human brain. And we've cut it so you can see what...
It's easier to explain the processes taking place in the distant stars than in our own heads.
Right above the ears is important for hearing. These lobes right here are important for making memories. The very top part is important in controlling movement.
That's one reason Helen likes to talk to school kids about what we do know. Great challenges exist in neuroscience. We don't yet understand how 3 pounds of tissue produce consciousness, how our brains turn into our minds and into our cells.
Okay, you can eat that part.
The brain may be the final frontier of science, waiting to be crossed by tomorrow's scientists.
Like making decisions? The left side is for controlling your right side.
There's a lot more of the brain that we didn't talk about. That's because scientists certainly don't by any means know what all the different parts of the brain do. That's why maybe some of you guys will grow up to be brain scientists. Because there's the most complicated structure in the universe, it's going to take a lot of people to figure out how it works.